Okay, hi everyone. So maybe just read this briefly yourself. Okay, so projection is how to get rid of the noise. And so you should have looked at these coding examples where we're given some data and we view them as our data set is a point in a 100-dimensional space. And then we pick like 4 functions and evaluate them at the x values, getting 4 vectors in that 100-dimensional space that span a 4-dimensional subspace. Our data is some vector here, and what we do is we project onto that subspace, and then we can use the 4 vectors to produce this projection, and that's in some sense the closest solution to an unsolvable problem. We can use the coefficients of these 4 vectors to combine our 4 functions, and then look at the graph of that function. And as you can see, it looks like a pretty good fit to the data. You can do the same thing in any number of dimensions. Here we're fitting a surface, which is given as the graph of a function of 2 variables, to sort of predict the 3rd variable. You can see most of these points are not on the surface. In fact, I think all of the points are not on the surface, but our surface still reproduces the data quite well, and it's the exact same process. Even when you do functions of more than 2 variables and you cannot draw the picture anymore, the linear algebra still applies. So what we have here, take a moment to read this part B. In other words, the way to read this is that, look, if you're trying to get to your data, the projection is going to be the closest of all the vectors in the subspace that you've chosen as a reasonable sort of approximation space. So you get to choose this subspace U, but once you choose it, and once you choose the inner product that allows you to compute these norms, then Pythagoras just gives you this inequality here. Okay, so let's see that. So if we take V, and then this vector down here is our projection of V onto the subspace U. And if we take any other vector U, and I guess I called this projection, I called it U tilde. We know that if we choose a finite dimensional approximating subspace, our data is probably not in the subspace. But it doesn't matter because the whole space can be written as a direct sum. And we're just going to throw away this piece, right? So our data can be written as a sum, and we're just going to throw this away and choose the projection as our approximation. Now, if we do that, what we have is we have a right triangle, 90 degrees right there, and the hypotenuse. And so this hypotenuse has a length v minus u. But that's, by Pythagoras, it's greater than this length. And it's only equal to that length when this part is 0, meaning u and pu of v are equal. Okay, in other words, their subtraction is 0. Okay. And so it's just Pythagoras, that's it. It's just you draw the right picture, and then this inequality comes out of Pythagoras. Okay. Take a moment to read number 10. Okay, so what's interesting is that these are 2 different answers, right? The Taylor polynomial is definitely in the space U, but according to this inner product, the integral, it's a worse approximation of our function. Okay, so the difference here is a local and global. If you have some function here doing who knows what it could be doing, and if you just want to approximate it sort of near this point here, then you should do Taylor expansion. The first term would be linear, the second term would give you a parabola that fits it, the third term would give you a cubic that fits it. Maybe it looks like that, who knows. So that'll be really good here, but it could be terrible over here and here. And so what's much better is if you care about it on this entire interval, then use the integral, and the integral will give you something that's close to it. Okay, so this is basically just which approximation is better and why. Well, it depends on your purposes. If you want the thing to be good everywhere, then you got to integrate these things. This is your inner product, and you should orthogonally project according to this. If you want it to just be good in a neighborhood of some points, like just very locally, then you should use Taylor series. Okay, you can think of that as coming from a different inner product or a different norm. So let's do the next one. Okay, so suppose that T is mapping from V to W. So now we're mapping between two inner product spaces. And B is something in W. Think of it as our data vector. Our data is B. And we need to consider solving for Tx equals B. So when is there a unique solution? Well, there's a unique solution exactly when the null space of T is empty. Okay? And there has to be a solution, but there's only a solution if B is actually in the range. Otherwise, there is no x such that Tx equals B. But if B is in the range, then there is an x. And if the null space of T is 0, then this is the unique x. Okay? Because if you had Tx equals B and you had Ty equals B, well then B minus B is 0, but Tx minus Ty is T of x minus y, and then x minus y would be in the null space. And so if the null space is empty, then x equals y. Okay, so that's a unique solution. Could there be infinitely many? Yeah, when B is in the range, then there is a Tx equals B. There is an x, but if the null space is not 0, you could take that x and you could add anything in the null space. And then when you apply t to it, you're going to get Tx plus Tn. This is 0, because n was my null space vector. And then Tx was a B, was a solution. So any x plus n will also be a solution to t times something equals B. If there are infinitely many, which one should we pick? I don't know. We'll pick whatever one you want. If, in many situations, you should pick the one of smallest norm. And then the answer will be pick the x that's equal to the adjoint. Oh, how do I do the adjoint? Maybe like this. The adjoint applied to B. So that we'll see in a moment, but right now you don't know what that is. Okay. Or maybe you do if you read the book. If there are no solutions, what should we do? Well, first just project our data onto the range and then solve for that vector in the range. That's the idea. That's what we've been doing this whole time. We should just take our data, and now it's B, and just project it down here, and then using our basis of U, actually solve, and we're good. I guess our basis would be here. Okay, so, all right, now